Hello everyone, my name is Mohamad Qadri, and I'll be presenting our work InCOpt Incremental Constrained Optimization using the base tree. We note that in many robotics problems, we have inherent hard constraints imposed, for example, by physics or geometry. For example, in manipulation, our estimates of the object pose should satisfy contact, and in navigation, estimates of vehicle poses should not violate obstacles. In this work, we try to investigate how to inject these hard constraints into existing estimation frameworks. Specifically, we focus in this work on problems formulated as MAP inference over factor graphs. In the literature, different problems have already been formulated as such. We consider three different examples where hard constraints could be used: planar pushing, 2D navigation, and 3D motion planning. As for related work, different solutions already exist to solve batch, factor graph constrained and unconstrained optimization problems. Our focus in this work is on incremental constrained optimization problems formulated as factor graphs where factors are continuously added as the robot explores the environment. Hence, for prior work, we primarily focused on two incremental optimizers, ISAM2, which is an unconstrained solver, and ICS, a constrained solver. To make them amenable to real-time performance, both ICS and ISAM2 try to reason about when relinearization is needed or how to perform fast matrix updates. ISAM2 moved away from the matrix representation of the problem and represented the linearized system as a base tree, which allowed for the use of fluid relinearizations. However, ISAM2 is an unconstrained solver and does not handle hard constraints. ICS is a constrained solver. However, ICS assumes fixed linearization points for earlier states and only performs batch linearizations at pre-specified steps. Hence, it's not suitable for problems which require frequent linearizations. Our proposed solver, InCOpt, is an incremental constraint solver which leverages the base tree and uses fluid relinearization. We split our method into two main components: the problem representation and the tree solution. First, let's consider the following constraint nonlinear least squares objective, where Fi, Gq, and Hp are all nonlinear functions of some subset of variables of x. We linearize the objective around the linearization point. Delta here is the state update vector. Capital A, G, and H are the Jacobians of the soft and hard constraints, and lowercase g and h are the constraints evaluated at the current linearization point. Now, we can write the augmented Lagrangian associated with the linearized objective. In this equation, VQ and UP are the dual terms associated with the equality and inequality constraints, ρQ and ρP are the penalty terms, and the max operator is applied element-wise. If we compare the constrained and unconstrained linearized objectives, we note that we have new quadratic and linear terms that appear associated with the hard constraints. And we also note that ISAM2 encodes this linearized objective as a Gaussian factor graph. Its QR factorization is represented as a base tree. Now, if we go back to the constraint objective and take special care in handling the maximization of the inequality augmentation terms, we see that all quadratic terms can be absorbed into a single quadratic system. We represent this new quadratic term as an augmented Gaussian factor graph since it encodes both the linearization of the soft constraints as well as the quadratic augmentation terms of the Lagrangian. The Lagrangian is now represented as an augmented Gaussian factor graph along with linear dual terms. Using this representation, the base tree can be computed using the same mechanism proposed by ISAM2. This example shows a factor graph with three hard constraints and how its linearization results in an augmented Gaussian factor graph. To solve the Lagrangian, we follow the derivation of Sodhi et al. To obtain the following iterative primal dual updates in matrix form. It is composed of a forward substitution to solve y, a back substitution to solve delta, along with dual ascent steps to update the Lagrangian multipliers. Note that in these equations, the R matrix and D vector result from the QR factorization of the large matrix A. Here we show the R and D matrices, which result from linearizing, then factorizing the nonlinear factor graph, and how the blocks of R and D are distributed across the nodes of the base tree. To solve for the Lagrangian, InCOpt converts all matrix operations to message passing over the base tree. We view forward substitution as an upward pass on the base tree. We distribute the blocks of y across the nodes of the tree, then each node updates its local vector y and computes residual vectors d, which are passed along with cached gradient information to the parent, and so on. We view back substitution as a downward pass on the tree. We compute the new state vector delta local to each node using the updated y vector and also perform the dual ascent steps. We first test InCOpt on a 2D navigation example where a point robot navigates a maze from start to end position. We incrementally add noisy odometry measurements, as well as unary box hard constraints on each post for ICS and InCOpt, and soft box constraints for ISAM2. We show the trajectory estimates of ISAM2, ICS, and InCOpt for 3 different mazes. We also plot the RMSD error and constraint violation for each algorithm. We see that InCOpt has the lowest constraint violation and lowest tracking error since it performs online relinearizations while handling hard constraints. We also test on a 2D planner pushing example where the objective is to estimate the pose of an object from contact measurements. We enforce equality hard constraints on the contact point for ICS and InCOpt and soft constraints for ISAM2 so that the probe is in permanent contact with the object. We see that InCOpt best satisfies the constraints and returns the trajectory with the lowest tracking error. We also test InCOpt on a 3D motion planning example of a 7DOF WAM arm where the objective is to plan a trajectory from a start to an end position. We use the GPMP2 motion planner, which frames the problem as probabilistic inference over factor graphs. GPMP2 uses 2 types of factors: Gaussian process factors to ensure smoothness of the trajectory, and obstacle factors to prevent obstacle collisions. However, the noise parameters of these factors need to be manually tuned. When the obstacle noise parameter is high, we obtain smooth transitions, but we may hit obstacles. When it's low, we do guarantee safety constraints, but transitions may not be smooth. With InCOpt, we can make the obstacle cost factors hard constraints. The resulting plan is smooth and safety constraints are guaranteed for any cost term. This is because InCOpt is agnostic to the noise parameters specified for hard constraints. To conclude, InCOpt is an augmented Lagrangian-based incremental constraint solver. It uses the base tree, which allows for fluid linearization, and InCOpt views all matrix operations as matrix passing over the base tree.